Alright, then, so let's try this one. So we have a periodic signal f of t that passes through a filter with frequency response of this equation. Right, so remember when you have a filter, right, so in this case, I just say this is the filter, right? You're sending us some sinusoids x or t, each at different harmonic frequencies. What happens is each frequency is affected differently due to the filter, or the filter changes the magnitude and the phase of each harmonic at that specific frequency. So you have y at t out. So for example, if x at t represented in the harmonic form, you just say a naught on 2 plus the sum k is equal to 1 to n at ak cos 2 pi k f naught t plus theta k are the outputs of the filter. Right, what happens is that each magnitude is multiplied by the frequency response, so the magnitude response of the filter, plus some k is equal to 1 to n ak by the magnitude response of the filter, and then each of the phases at that specific frequency will be added to the phase response of the filter. So all in all, you have a sum of sinusoids going in. You'll get back a sum of sinusoids, but each magnitude will be multiplied by the magnitude response of the filter calculated at that harmonic frequency, and each phase will be added to the phase response of the filter, and again calculated at that harmonic frequency. Right, so the filter is frequency dependent. Right, depending on the frequency that you send into it, it will affect the magnitude and the phase of that specific sinusoid differently. Right, so in this question here, they gave us the frequency response of the filter here. So they want the Fourier expansion of the signal at the output. So the only thing we are missing right now, we don't have the magnitude response and we don't have the phase response as yet, but we can calculate it. So the first thing we need is the magnitude response. So the magnitude response will just be the magnitude of the numerator divided by the magnitude of the denominator plus 3 omega on 10. So remember, magnitude is the square root of the real part squared plus the imaginary part. The numerator has no imaginary part, so that'll be the square root of 1 squared. The denominator will be the square root of 1 squared plus omega on 10 squared. And we could reduce that. This will cancel with the square roots. So we get 1, and 1 squared is 1, and that'll be omega squared on 100. So that'll be the magnitude response of the filter. But the second thing we need is the phase response of the filter. So the phase will be the arguments at the top divided by the arguments of the denominator, right? And by the rules, there will be the arguments at the top subtract the arguments of the denominator, right? So that'll be, so we have tan inverse, or the imaginary, in this case is 0, on the real, that is for this piece here, subtract tan inverse of the imaginary, which in this case is omega on 10, on the real part, which is 1, Right. Tan inverse of 0 and 1 is 0 because if you draw an argon diagram, the argument is basically the angle measured from the positive real axis, which is this here. So if we were to plot this, the imaginary part is 0, so it has no vertical and it has a horizontal. So therefore, the argument would be lying on the x-axis itself. So the angle from the x-axis to the x-axis is 0. That is why this piece here is 0. Right, and then this piece here, it would just stay as tan inverse of omega on 10, because omega is 2 pi f, and f is the frequency that is sending in to the filter, hence you could see how it is changed. So therefore, we could just remove the 0, and that will be the phase response of the filter. So now we could finally plug it into the final form. So wire t, let's zoom in. Right, so wire t would just be, so you have a naught and 2. You have to multiply that by the magnitude response, which was 1 on the square root of 1 plus omega squared on 100 plus some k is equal to 1 to n ak